Greetings to all of you. This is General Physics 2. This is week 10, and the subject is AC, alternating current, circuits and such. And this is lecture part 1. So I'm going to go to the notes. I've posted these as well, just as documents you can look at, but here I'm going to be walking you through them in some detail. So AC circuits, we start with what we had last week. We had a generator which consisted of a loop of wire with a magnetic field going through it, and this loop was rotating on an axis. And by rotating like that, that generates an EMF. And that comes from the idea that flux is the area of the loop times the B field, and the B field through the loop would be varying because of the angle changing as the loop changes. I wrote it as a sine function here. You could just as easily have called it a cosine. That just depends on when you start the clock. So this one I happen to write as a sine. And if that's the flux through the loop that is varying sinusoidally, going one way through the loop, then the other way through the loop as the loop rotates, then you get an EMF induced in that loop, which is the area times the B field. And because you're taking a derivative, you remember the EMF is the derivative of the flux. And so that derivative brings out this factor of omega so that it's out in front as well. And so then you have an EMF that is itself also sinusoidal, and the peak value, the EMF max, is the area of the loop and the B field and omega, the speed. That's all from last week. That stuff we did. The point of all this, though, is that what you get then is a source of EMF that is it's changing, it's varying. So this EMF, remember, an EMF is kind of like a voltage. So it's a little bit like having a battery here, but a battery whose voltage is changing and in fact reversing. So it's going back and forth one way and the other. So this is the new symbol for that. This is an AC source. This is the kind of thing you get if you plug something into the wall. What you have there is of sinusoidally varying voltage. And then you can connect that up to different things like a resistor, as I've shown here. And now what I want to do is some stuff that really is kind of funny. Nothing odd happens in this case, but I just want to show you why we pick some rather strange ways of defining what the value is. When you've got something varying sinusoidally like this, you might have to say, well, how are we going to say, how big is it? What's the voltage? Well, the voltage is varying all the time. But if you know that, you still want to be able to characterize it somehow. And we have kind of a strange definition for that. It has some good reasons for it, but I'll get you there. So let's just take a look at this kind of a circuit and look at what happens when you connect either a battery or an AC source, like we've been talking, to a resistor. If you look at connecting a battery to a resistor, then we have Ohm's law, V equals IR. You could talk about EMF, and we talk about the EMF of a battery. That's the voltage, the pure voltage that it's trying to produce apart from its internal resistance. That is often called the EMF of the battery. So the EMF of the battery equals the current times the resistance. And if you want to solve for current, you just get 1 over R times the EMF of the battery, the voltage of the battery. Over on the AC side, everything looks the very same. V equals IR, EMF is I times R. So solving for I, it's 1 over R times the EMF. But this EMF, recall, is changing with time, and that means the current is going to change with time. So let's put that full expression for the EMF. If you recall back up here, I had this EMF. It was described as some maximum value times cosine omega t. So I'm putting that same function in right down here. This maximum value is sort of like the amplitude times cosine omega t. So you can rearrange this ever so slightly to say the current now is this EMF max divided by R times cosine omega t. That again looks like a cosine function with a sort of amplitude out in front of it, and we could call that the maximum value of the current times cosine omega t. Everything, by the way, here is in phase. That is, when the EMF reaches its maximum value right here, the current will also reach its maximum value. That's what you would expect, and that's what happens. And you can kind of rewrite this just dealing with the maximum and say the maximum current would be the maximum voltage divided by the resistance. There's nothing surprising here. All of this is what you might have expected. Now let's look at power. This is when we first get some surprises. Excuse me. For power, recall that power is current times voltage. For DC, it's just this, and if you happen to have a resistor, it would be I squared times R or V squared over R. These are all different expressions to get power. For AC, the trouble is it's varying with time. It's still true that the power at any moment, the amount of power being dissipated at that instant, is current times voltage. That's always true. But now we can put in expressions for this. So I just a moment ago derived an expression for the current. It would be I max times cosine omega t. And the voltage, this could be EMF max. Here I've switched to V. I'm not sure why, but so now we're going to say V max times cosine omega t. And you could rearrange this expression. I've just simply substituted in I and V. They each are varying with time. And so now you've got I max times V max times cosine squared of omega t, because both of these are varying cosine by a cosine factor. You end up with cosine squared. That has an interesting effect. It means that here's a graph of V is the red curve and I is the green curve. There's no meaning to the fact that I is smaller than V. They're on different scales. They're different quantities. I've just put them on the same time graph so we can see them. The point is to notice they both reach their peaks at the same time, and they're in phase. So when V is positive, I is positive, and so the power is positive. But interestingly, when I and V are both negative, P is still positive. So you get lots of power right here when the voltage and current are both positive, but you get the same amount down here when they're both negative. So if you look at the power, it's going up and down, but it never is negative. It's always positive. So it goes through these little bumps, actually goes through a bump twice for each full cycle of the current and voltage. So that's kind of interesting. You've got power that's always positive, which makes sense if you go back to the original circuit and just imagine that you had switched the battery and made the current flow the other direction. The resistor would still be using power. It wouldn't be giving up power. It would still be using it. The battery would still be supplying power. The resistor would still be getting hot. It wouldn't be getting cold. So it doesn't matter which way current flows. The resistor gets hot and it uses power. So that maybe explains why the power is always positive here. Now, this power is sort of going up and down. It does have moments of zero when the current and voltage cross through zero. Then for an instant, there's no power being dissipated. What often is of much more interest than trying to see what the power is doing at one instant is what is the average power. So let's see if we can calculate the average power. So here's average power. That's going to be taking this expression up here and trying to average it out. Well, you would have this maximum current times maximum voltage, which would be the maximum power. The instant when you have the maximum value of the power, that's when cosine omega t would be 1, and so this would just be the maximum value. But if we're trying to get the average of this, that's just the peak. And what we want to do then is figure out what's the average of this cosine squared function. It's oscillating up and down like this in a funny way. And it turns out, you look at that and you say, wow, that looks an awful lot like a cosine function that's twice the frequency and shifted up a little bit. And in fact, that's what we have here. Here's cosine of twice the frequency, 2 omega instead of just omega. And there's an offset of exactly 1/2. So this goes up to 1, or at least the cosine squared function would go up to 1 at its maximum, down to 0 at its minimum. But the whole thing is shifted by 1/2. So if we're just going to take the average, this bar over here is just trying to indicate we're taking an average. If we're taking the average of this whole thing, the cosine of 2 omega t here, that's going to average to 0. That's just the up and down part of this. The 1/2 is this average level that you get in there. So the result of all that, doing your trig of cosine squared, and it wouldn't matter if we did it with sine squared, you get the same thing, is this extra little factor of 1/2 here. So what we find is that the average power is exactly half of the peak power. So this has some interesting implications. So now we know that the average power is half of the peak power, and the peak power, the maximum power, is just the maximum current times the maximum voltage. All right, now let's go to the next page and introduce this idea of RMS. First, playing around with this just a little bit more, if the average power is just half of the peak power, that's half of the peak current times the peak voltage. And we could, if we wanted to, be perverse, take this 1/2 and express it as 1 over the square root of 2 times 1 over the square root of 2. So I haven't done anything special here. I've just taken the this 1/2 and split it into 2 factors and regrouped things a little bit. And now that starts to look like something kind of interesting here. Doesn't this look like current times voltage, but with a factor of 1 over square root of 2 on the current? Instead of I max, it's I max divided by the square root of 2. And instead of V max, it's V max divided by the square root of 2. You could also do this with the other formulas that we have for power. It is also can be written as V squared over R, but you've got this factor of 1/2. But if you wanted to, you could put that under the square here. And so say it's 1 over the square root of 2, which you then square, you'd get the same thing. Do the same thing with the other formula for power, I squared times R. This factor of 1/2 that came from here, we could stick into here. So now you'd have to remember all these weird formulas. Do you have factors of 1/2 or factors of 1 over the square root of 2? Well, there's a way around having to learn a new set of formulas for AC. It's kind of an odd approach, but what we do is we don't quantify current and voltage when they are AC by the peak. We don't use I max and V max. We use something called RMS, which stands for root of the mean of the square. So the IRMS is the square of I, and then you take the mean of that, and then you take the square root. You sort of do it backwards from the way we say. You take the root of the mean of the square. So let's try that out. Here's I. If we start with I, we're supposed to square it. Remember, our formula was I max times cosine omega t. So if we square that, we got to square everything here. Then you have to take the mean of this. But taking the mean, or the average, the time average, taking the time average, this value is always the same number. It's just the peak value. And the time average of cosine squared omega t, again, is just 1/2. That's where you get that factor of 1/2. So this IRMS, I squared just ends up, this whole IRMS, well, wait a minute, okay. So that was, here it was squaring it, then I was taking the mean, and the next thing I've got to do is take the square root of it. And so that's going to be the square root of what I just found here. And that is just 1 over the square root of 2 of I max. So the RMS value is just 1 over the square root of 2 of the peak value. And the same thing is true of voltage. You could go through the same argument, you get the very same result. So that the RMS value isn't the peak value, it's a little less than the peak value. For example, if your RMS value is 120 volts, then the max value is the square root of 2 times the RMS. Here it's dividing by the square root of 2. Here I'm going the other direction. I'm starting with the RMS value of 120 volts. The reason I'm starting with that is that is the line voltage. It's 120 volts. You probably all have heard that. But what you haven't realized is that is not the peak value. That's the RMS value. The maximum value, you'd have to invert this formula up here and take the maximum. You would say the maximum is equal to the square root of 2 times RMS. So here I'm taking the square root of 2. So the peak value is actually 170 volts. Okay, so now to just kind of review, why did we do all of this? The reason is that if all you ever do is talk about RMS values, VRMS and IRMS, if you calibrate your meter and if you always quote the specs and everything is RMS, then when you try to calculate the average power, you just take IRMS times VRMS, because that already takes care of that factor of 2. Each of those has within it 1 over the square root of 2. And you multiply them together and you get the factor of 1/2 that you needed for the average power. If you look back up here in these average power, that gets us that factor of 1/2 without having to put it into the formula. So just to reiterate, it is true that when you use a meter and measure the voltage and you set the meter to read the AC voltage, it is reading RMS. You didn't know that perhaps, but it is. That's the number it's giving you. When you read on some device that it's meant for 20 volts AC, that means 20 volts RMS or 12 volts AC. VAC is a way of just saying VRMS. They very rarely write it as RMS. It's usually just written as AC. But essentially, that's what you'll always see. That's the way it's always quoted. And now you can just use all these formulas like we did before. I squared R, V squared over R, or I times V. All of these work to give you power. Understanding that you're using RMS values and that you're getting average power. You're not dealing with peak anymore at all. Now, all of this only applies, well, it all applies. These rules apply to anything if you're using RMS. Just beware that the relationship, this 1 over the square root of 2 relationship between the RMS value and the maximum value, that's only true if it's a sinusoidal waveform. Here, for example, is something that is not, just to show you a different example. What if we had a waveform that alternated between 0 and 4 volts? So that half the time it was 4 volts, half the time it was exactly 0. What would the RMS value of that be? Well, half the time it's at 4 volts. What we have to do is go back and take, now remember it's root mean square, but you do it backwards. You start by squaring it. So it's half the time, v squared is 16. The other half, it's 0. That's the squaring. Now we have to take the average. That's 8 volts, because it's half the time at 16 and half the time at 0. So the average is 8 volts. And then finally we take the square root of that number to get the final value. Square root of 8 is 2 root 2, or 2.8 volts. So if you had a waveform like this and you were asked what is the root mean squared of that value, you'd have to say, well, it's 2.8 volts. That would be the RMS value of this particular waveform. All right, that is where I'm going to stop and divide this up into pieces.